Okay, order statistics. We all know what a statistic is. We want to know what an order statistic is. As the name insinuates, it is a statistic obtained after ordering. In other words, sorting. You put them in order and you use or you compute a statistic using ordered data. We know some ordered statistics from undergraduates starts at least one for sure. What is that? One ordered statistic that we know.
I'm trying to think real quick. This, like with standard deviation, does the order matter? No. Like, mean the order doesn't matter. Does it not? Median.
Median. How do we find the median? We find the median by putting the data in order, descending order typically, and we come up with the median for the data. So examples. Minimum is an ordered statistic. So is maximum. Median. Percentiles. Within percentiles, we have quartiles, quintiles, deciles, ... So quartiles, quintiles, deciles, they're all percentiles. The percentile would be the generic term. Quartiles are simply percentiles that are measured as every quarter. Quintiles, P5, P10, P15, P20, every fifth. Deciles, P10, P20, P30, P40, and so on. Good. Now, if we consider a sample with size n, those are all random variables. That's just how we do things in statistics. So x1, x2, x3, all the way up to xn are IID random variables. From a finite distribution, mean mu and finite variance sigma squared.
What do you mean by finite distribution?
It has a finite support. A well-defined distribution. Now, it could have infinite support, for instance, Normal distribution goes from negative infinity to positive infinity, but it doesn't have a point mass that, spikes at one value. It's a well-defined distribution. A normal distribution is a finite distribution, or a distribution with infinite support, but a finite distribution. So if we collect a sample of size n, if we draw a sample from this distribution, of course, the distribution is going to have some mean and some variance. Each random variable will follow that distribution. Do we agree? So if x1, x2, x3, all the way up to xn, they're all drawn from, say, a normal distribution with mean 10, variance 2, then x1 drawn from normal, x2 drawn from the same normal, and so forth. So theoretically, x1 will have the same, for instance, if I call it normal mu sigma squared, x2 will have the same, which is why we always denote
But if they all represent, if x1 through xn represents theoretical distribution, then don't they all have the same theoretical distribution? That's good, right? But they all just equal each other.
they all will come from the same distribution, but they won't all be the same value. If you say, I have 4 variables, they're all identical algebraically, then my conclusion would be x1 is equal to x2, equal to x3, equal to x4. But if I say x1 through x4 are drawn from the same distribution, for instance, mean 10, variance 4, as an example, do you think that x1, x2, x3, x4, they would all have the value 10?
Or at least really close to it.
Yeah, close to it, but would they all be the same?
That's what I'm not sure, because they're sampled, right? Don't they reflect the variance in the samples? Or are they all the same? Because I mean,
When they say LIT, they all have the same distribution. Like a density CTM. Would they have the same value?
no,
No. They're going to come from this. Yes. Suppose x1 and x2 came from a normal, mean 10, standard deviation 2. And let's say x3 and x4 came from another normal.
and we mean x1, x2, that's the functions, the random variable, right?
Come again?
When you say x1 and such, do you mean the random variable as the function, or do you mean like
It's just the random variable, the observation that you get.
that's why I get because I read in the theory for different classes, the random variable itself is a function, and the observation comes from the random variable.
The random variable. So I think you're confusing it with, set theory and how we go from a set to a variable, right? If you take a random variable, it maps a set onto a different set, right? It becomes a function of that set. Right, for example, I can say I can define a random variable x1, which would map the interval 0 to 2 with some probability to 100 to 200. Yes, in which case it is a function. You can create functions of random variables. So if
Which you call the observation of like the image of a random variable. Is that also, would you call that the random variable too? Sorry, a little.
identity map. Yes.
Yeah.
Right. If x is a random variable, g of x is also a random variable,
Okay,
right?
I see it.
Simple identity map. So which is why, people like to call function a random variable. Why? Because they often use functions of random variables, mean there's a function of random variables.
Like f of x, the random variable of. No, the function of the random variable.
Yes. So if you take mean, for instance, it should be f of x1, x2, x3, all the way up to xn, function of random variables. Yes. And what is that function? You sum all the x values and you divide by n. Yes.
Yeah.
I can change this, come up with a different function. G of x is equal to x squared. X squared is a random variable. If x is random, so is x squared. Yes, so I can form functions of random variables. But what we've got to keep in mind is g of x equals x is a random variable. So identity map. So if we have xi drawn from some normals, for instance, IID, mean mu variance in the squared, it doesn't mean that every single observation, x1, x2, all the way up to xn, will be the same value. We say identical variables, yes, they're all the same. Identical random variables drawn from a distribution would satisfy that. Great. So the random variable of xi, a good well-defined distribution, would simply mean that we have a probability distribution function, probability density function. Yes, and corresponding to the probability density function, we would have a cumulative distribution function. So we've got the PDM, and we have the CDM. Yes? The rest is fine. And we all know if you take the derivative of the CDM, you get the PDM. if you integrate it, you'll get the CDF. So far, we've got this sample drawn from distribution. It has a PDF, got the corresponding CDF. All of that is set. Now here is the question. Suppose if I order the sample or sort the sample. So in other words, I'm simply putting the observations and arranging them in descending order. Once I sort, I have to distinguish it, but in terms of notation, which is why I write it this way. It's very common to use this notation. That's it.
And those. Are you confused? We're talking about the random variables. That, which is sample, right? So we're all.
The observation is the random variable.
And all the prior classes I've had, we haven't really treated it. I don't know, it seems like we've always kind of treated it as.
We'll just have this one. Will xi, I being within parentheses, follow the same distribution as the random variable xi? Xi is the ordered statistic, and xi is just a random variable.
Well, when we look at the distribution, it's always with that ordered x-axis, right? I mean, how would you look at the distribution without ordering? So
Okay.
every distribution group.
So your argument is that, the axis has a natural order, so every observation has a natural order. Again, you're looking at it from the perspective of a number, right? When you have a distribution defined on, so let's take the same example, 10, 12, 14. If I draw observations from that interval, and I say it's normally distributed mean 10, variance 4. And I ask you, oh, give me a number. Give me a number. 9. Another number.
15.
15 with very low probability, but it would happen. Could. Another number. 12. 12. Okay, another number. 7. Another number. 8. Another number.
8 again.
Okay. All of these numbers will follow the same distribution. Do you agree? 8 came from a normal. 12 came from a normal, same mean variance. 15 came from the same normal distribution, mean variance. Yes? No. That raises the problem. So we started with the number 9. Yes? And what else?
I think it was 15,
15,
7,
7,
2, 8,
2, 8, give me a couple,
12,
12, 10.
there's a 9 in there.
Why integers? Can't give me decimal values.
9.1,
9.1.
2.1.
Good. That's a sample. Yes. Every one of those observations came from a normal distribution. Supposedly, I don't think that's going to follow a normal distribution. But what makes it from there? Right? No. No matter what observation you pick, they all came from that distribution. Going to solve 7. Oops. 5. That is the sorted answer.
I guess I was trying to ask is, aren't distributions inherently ordered?
Do you mean values? Inherently ordered?
In order to have a distribution of some kind?
Sure, here. You're confusing the axis with the sample that you draw. When you draw a sample, does it have a natural ordering? In other words, you have a 6-sided die. When you keep on rolling that die, do you always get 1, 2, 3, 4, 5, 6? 1, 2, 3, 4, 5, 6? No, you get a bunch of numbers, correct? Same thing. If I draw from a continuous distribution, do I always get 6 first? 6.0001, 6.0002. Do I go in that order? No. I'm sampling from this interval. It could be any number. That's what we mean by sampling from that distribution. See the difference?
I was just been wondering if you could have a distribution if the data can't be ordered. You really have a distribution.
That can't be ordered.
Yeah, like categories or something.
Oh, yeah. I mean, when you have categorical data, you can't come up with the density theory. Right?
So then wouldn't it kind of like imply that if there is a distribution, then it's already like ordered?
If there is a distribution, there is a support,
Okay.
right? If you have a discrete distribution, a discrete random variable, it has a support. A continuous random variable has a support. Normal distribution, negative infinity to infinity. Yes. Exponential 0 to infinity. Uniform, if you say 0 to 1, the support is 0 to 1. Yes. So they all have a support. But that's not what we mean by order here.
So, do you mean would the distribution of samples follow the distribution of the variables? Is that what the question is?
No. Would the distribution of these, each of those, be the same as those?
Yes, of course, right?
I mean, yeah, because it feels to me like we're taking something from just a distribution, and we're just I don't understand why they wouldn't be. Cause I mean, if we, like, I get that we're putting them in a different order, but. Those numbers, like, yeah, what's saying, like, they still came from the normal distribution, like, where else are they coming from?
Right, I agree. But you're answering a different question.
Yeah, that's, I guess we don't understand, right? Yeah. I don't.
So. Each of those x's come from a normal distribution.
Yes.
If I ask you, well, what is the probability that x7 is greater than 10? What would your answer be?
Oh. Well, it would be less than 50.
Yeah.
Oh, no, it would be 50, exactly.
50%,
Yeah,
right? If I asked you, well, what is the probability x2 will be greater than 15? Very small,
right.
right? Way past 50, small probability, yes. But if I change problem and I said, well, we have this sample that came from this normal. Yes, mean 10, standard deviation 2, that means 4. If that is the case, what are the chances in a sample of 9 observations? The 5th observation is greater than 8. Nine observations in order. If you sort it, what are the chances the observation that falls in the 5th position is greater than 8?
For this particular sample, it's 100%.
Yes. Huh?
It's 100%.
Yes, right?
Right.
For this one, it's 100%. Now pick up your calculator and tell me what the probability. Well, what is the probability if you look at this and say the probability x is greater than 8?
Yeah, you have to use your some kind of z.
Oh, just by counting. Let's just count. Well, what's the probability x would be greater than 8? I believe it's 7 out of
Yeah.
9. Yes, that's 7 out of 9. Over here, it's 100%.
Oh.
But clearly the probability is not the same. Here we are answering the question, what are the chances that this particular position in a sample of 9 observations observed or sampled from a distribution would satisfy a condition? So here I'm saying, well, if I draw 9 observations from a normal distribution, put them in order, what are the chances the 5th ordered statistic will be greater than 8?
100%.
Here, 100%.
So it's
Oh, wait a minute, it's not 100%. No, the 5th observation is greater than 8. This one.
1, 5, 9, 5 out of 9.
1, 2, 3. Yeah, it's 5 out of 9.
So then what was it back up there? again?
7 out of
What are the chances that x5 will be bigger than 8? We're saying 100% by looking at this value. But how do I put it? Would it be the same for every single sample that you get?
No.
No, right? If you obtain a different observation, or excuse me, a different sample, you will have a different value in this position. Yes, so you would end up getting a different distribution. Perhaps R would be good here. Okay, so this is what I'm going to do. Let's say I come up with a sample. 10 observations, mean 10, standard deviation 2, oh, there's 16 observations. No, how many do we have? 9. Good. Now, if I want to form a density or a distribution, I've got to repeatedly see what comes in this particular position. Do you agree?
Oh.
If I don't care about position at all, it's just a sample. No matter what sample I draw, it is coming from a normal. Every single observation is coming from a normal. But I'm going to start with the first one. I want to form a density, so let me set a seed. Set a seed. And I have to repeatedly observe multiple samples to get the distribution of this ordered statistic, which is minimum. Yes? But in theory, we don't have to do that. We have ways to compute it. Are they messy? Extremely messy. Non-parametric statistics revolves around ordered statistics. An entire field. So oftentimes coming up with an exact distribution is difficult. So you have to rely on simulations, like I'm about to do, right? Distribution for mean, sampling distribution for mean. We know what that is exactly. It is normally distributed. You know its mean, you know its variance, easy to derive. But if I asked you to find the sampling distribution of the median, not so easy, right? Because the sampling distribution of the median is going to depend on the sample size. Yes? And you have to derive using that.
So-
Okay.
So
Yes.
when we're asking, does X ordered I follow the same distribution as I? We're not talking about the whole sample, we're just looking at what is the distribution of X1?
Yes.
And in this case, very, very highly likely going to be a normal curve.
Yeah, we will see.
Right, and then I would guess, right, for X1, the minimum, most of the samples are gonna.
Oh, sorry. We'll see. So here I'm going to show how to come up with the distribution of X1 against the ordered statistic of X1 now. But regardless if I want to come up with the distribution, I need to, sample multiple times. So, let's see.
So you're gonna store all the medians, you can do like 100 samples. And
No, I'm just going to start with the minimum first. So, two of them, US and S. S for sample sorted, US unsorted. And I'm gonna do it 1,000 times. Good. And in here, first I'm generating a sample and collecting 9 observations from a normally distributed population with mean 10, standard deviation 2. The very first observation I am going to save in US, the unsorted vector. Yes. Why is this sorted, by default, it's in descending order, we always do ascending order. So, we'll put it in ascending order, so I'm going to sort the sample that I have. Save the first observation of the sorted data to y. Excuse me, y of 1 to s of k. Yes, I could have done minimum also, but I'm going with, x1, so I'm sticking with that. Good. What may so far? Do we follow the code? So, goal is to demonstrate the distribution of the statistic is going to, the distribution of x1 of the sample will be different from the distribution of ordered statistic x1. The xi's are all identically distributed. However, the ordered statistics for any I, they're not identically distributed. That's the goal. Good. So typically we use histogram to visualize let's see, so or shape. So the unsorted if I run this, what would the distribution look like? I'm going to plot the histogram of unsorted data. So unsorted data, but only the first observation. The first observation, unsorted.
Well, if it's unsorted regard, it's irrelevant if it's the first observation, right?
Right,
So it's normal.
it'll be normal, okay. Good. Let's pick the 9th observation. Unsorted. Yes, what would it be? The 4th observation. Not normal. Still normal. So no matter what observation you pick, it is going to be normally distributed, same distribution, in the sense bell curve, mean 10, standard deviation 2, in other words, the variance is 4. Now, of 2 is sorted. Let's start with the first ordered statistic. Its mean is about 6.5. The about 4 over here, 10 over there. So is it a bell curve? Looks like a bell curve. But the mean is about 6.5. Now, for the 9th order statistic, y9. Normal distribution still more or less looks normal, but what does its mean? Its mean is 13, and variance.
So what's the pros and cons of playing with the size? Why sub, whether we're looking at the max, the min, or where that, or how many numbers we're using. I guess I'm wondering how to like are there any pros and cons of, like, using bigger?
What do you mean pros and cons?
Because whether you, because right, the min and max are gonna change depending on the size of the sample, right? And then
Yes.
And then on top of that, when we tried to look at the actual median, the median didn't match up with the actual mean. Wouldn't you want that to match up. So wouldn't that indicate the trite, now, I don't know, never mind.
I mean, in the long run, mean, median, they would, you know, converge and be the same. And that's why we have convergence in distribution, convergence in probability and all of those. You know, when you have a really large sample, things are going to change. Right? In the sense that if you had different mean and median, for example, a skewed distribution, if n approaches infinity, it will be skewed n, right? For a large sample, it'll just converge to a normal distribution. Skewness will go away. But you can't justify removing the skew in every single possible example that you can think of, or application that you think of. In some cases, that skew is probably important, right? But that's basic, you know, that's where, you know, we keep the prior information. We don't simply approximate it and say, oh, and it approaches infinity large sample size,
Right.
we will use normal. Okay. The distribution of the maximum happens to be normal, mean 30, as expected, it has to be on the upper end. Right? Let's look at the distribution of the fourth ordered observation. Now we call it an ordered statistic because each observation is a statistic in and of itself. Think about our regular joke that we often, you know, say, I don't want to become a statistic, right? If you say, oh, someone at the age of 16 has a certain chance of getting hit by lightning during a thunderstorm, and if you're 16 years old, you'd probably say, I don't want to become a statistic, but you are an observation, correct? So every observation in a sample is a statistic. It becomes more of a statistic when you put them in order and makes better sense, right? So that is X4. According to the data, now, we wouldn't be able to say this from the sample itself. Yes, but what the ordered statistic tells us, if you are drawing a sample from this distribution, the fourth observation in a sample of 9 observations will follow that distribution. It will have a mean of 9.5 and some variance. If you change it to the second,
Is there a way to calculate all this without having to brute force it?
yes, there is. We'll have 8 for the second observation. So that's where I was planning to go today. To derive the distribution of minimum, maximum, and any ordered statistic. But it's a good thing we did it this way, so you know the difference between the distribution of xi and the distribution of the ith ordered statistic. Yes. So are they the same? Absolutely not. They cannot be. So no. There are ways to find the distribution we are going to derive, but as I mentioned, ordered statistics are quite hard to compute. Densities of ordered statistics are quite hard to evaluate or compute. There are certain situations where things become slightly easier, and that would be IIT. identical is sort of is given, right? We want a sample to be drawn from the same distribution, but the key thing that would make finding densities of ordered statistics easier is independence. If we don't have independence, you have to find a joint distribution. In the sense, if someone asks you, well, what is the probability that the fourth ordered statistic is greater than 8? And the seventh ordered statistic is less than 10. Right? If they're independent, things are easy to find. But if they're not independent, this is going to depend on that, and things are going to get complicated. So we're going to do the independent case.
Is it